Hi, and welcome to 8.4 Gravitational Potential Energy. In this lesson, students will be able to describe and calculate gravitational potential energy. But first, three questions for you. Number one, would you rather drop a bowling ball on your foot or drop a marble on your foot? And why? Why do you think so? You might have said, the bowling ball has more mass, so I would rather drop a marble on my foot. Thank you very much. Okay, so mass has something to do with your answer. Now, I'm forcing you to drop a bowling ball on your foot, unfortunately. Would you rather drop a bowling ball on your foot from 10 centimeters or drop a bowling ball on your foot from 10 meters? To picture that, picture 10 meter sticks. Meter sticks are close to a yard, so maybe 10 yards up. Would you rather set centimeters or meters, right? So height has something to do with it too. I hope you would rather drop a bowling ball from 10 centimeters if you had to choose. Final question. Would you rather drop a bowling ball on your foot on the earth or drop a bowling ball on your foot on the moon? Take away the fact that it would be fun to be on the moon, right? Either one, I'll give you a trip to the moon, but you have to drop a bowling ball on your foot. Choose one. Hopefully you choose the moon. Why would you choose the moon over the earth? Because the moon has less gravity. There's still some gravity there, but there's less. It's about 1/6 of the gravitational field strength on the moon than on the earth. So we have these three factors here that have to do with our bowling ball dropping choices, M, G, and H. Let's see how those play into doing work against gravity. So you're lifting an object upward with a constant velocity near Earth's surface. We've seen scenarios like this in word problems before. It says how much work is done on the object, and we've kind of been dancing around it. And I just say, okay, you're exerting a force that's equal to the weight of the object because you're moving at a constant velocity. All right, so you're doing work. You're going to exert a force. Look at this person. They're going to work really hard. They have to do some work. They have to exert a force over a distance. So they are doing work. And before, in the last episode, we said, like these are very entertaining episodes. In the last lesson, all right, we said by exerting a force over a distance, you can increase the object's kinetic energy. So the work was equal to your change in the kinetic energy. That's where the work went. It went into kinetic energy. Now we're doing work, and where did that work go? Where is that energy going? We're moving at a constant velocity, so I'm not changing my kinetic energy at all. Where is that energy going? We'll see that it's going into gravitational potential energy. So the work is equal to the force times the distance. All right, so what should the F be in this case? Well, in Newton's second law, you can use this to determine what Fg is equal to. So Fg is equal to mg, and we'll plug in mg for F. All right, so we have mg times d. Now this is probably going to be the easiest one. Yes, we moved it a distance, but if we're always talking about planet's surface and we're talking about lifting it up, you could say height instead of distance. So we'll use the distance is equal to height in this case, and we'll just switch out the d for the h. It's still the same thing. It's measured in meters, all right, but they like to use h when talking about height instead of the distance up. Okay, so now we know that the work done is equal to your change in your height times your mass. So if you have more mass, it's more energy stored up there, times the gravitational field strength. If it's a stronger gravitational field, you're going to have to do more work. And we said the work that you're doing is equal to your change in your potential energy. And again, it's a change because you're just changing your height above some ground level. So two key takeaways. The work is equal to the change in the potential energy Very similar to the work kinetic energy theorem, but instead of getting faster or slower and changing our kinetic energy, we're changing our height above some zero level in a gravitational field. All right, and we have mass. All right, and then this also tells us what the formula for gravitational potential energy is. This is what it looks like in the reference table. Okay. So just as a side note, just keep in mind there's two different types of potential energy that we'll talk about in this class. Potential energy in general is energy an object possesses due to its position or condition. So the position of this boulder in this gravitational field gives it some gravitational potential energy. If it gets tipped over, then that gravitational potential energy gets transferred into kinetic energy as it falls down. It loses gravitational potential energy. That potential energy gets transferred into kinetic energy. So it's potential. It's stored. Some people say it's stored energy. All right, you have this all built up because somebody lifted this up and put it on top of that cliff. By doing work, they had to lift it up and put it on top of the cliff. They're storing that work. They're storing the energy there. Very similarly, this is showing the shocks in a car. Some shocks look like this, others look different. It's just a metal bar. That's what most people have in their cars, but this is showing us a type of spring. So the next type of potential energy we'd talk about is elastic potential energy. And just as a sneak preview, yeah, to compress a spring, you need to exert a force over some distance. So you're doing work on that spring, and the work that you do is stored in the spring. The spring has now potential to do work. The spring itself can transfer the elastic potential energy into kinetic energy and cause something to move. It's stored up. So the work that you do in pushing the spring is stored in that spring. And the work that you do in lifting an object in a gravitational field is stored in that object, in that gravitational field. You have stored energy, potential energy. And remember, potential energy is a type of mechanical energy. All right, mechanical energy is just kinetic and potential. All right, and there's two different types of potential. We're not going to learn a new equation for mechanical energy. It's an umbrella term. So this is gravitational potential energy, and I like to use GPE to differentiate it from the other potential energy that we learn, elastic potential energy. It says gravitational potential energy is the potential energy stored in the gravitational fields of interacting bodies. GPE depends on height from a zero level, which normally you make the ground. Depends on what your analysis is. So here's the check. If something is above the ground, it has gravitational potential energy. If something's hanging out in the air or above the ground, if it was on the cliff and it's going to fall down, then it's above the ground, and you could say that it has gravitational potential energy. Just as a review, do you remember what the check was for the kinetic energy? The check is if the object is moving, it has kinetic energy. For this one, if something is above the ground, it has gravitational potential energy. What do you think we should make the units for gravitational potential energy? Luckily, it's still joules. It's a type of energy, so we just measure it with the same unit, joules. And here is that formula. All right, GPE is equal to mgh. We derived it on the previous slide. All right, and it says, how can we change this formula? You take out mg and you replace it with the force due to gravity, the weight. All right, so we have this. GPE is equal to FGH. Now don't multiply by g here. This is just a subscript. This is saying the weight of the object times the height. All right, so if they tell you what the weight is in the problem in newtons, then you could use that many newtons and just multiply it by the height, and that'll give you the energy. It's kind of a shortcut. Instead of changing the weight that they give you into the mass, and then you just multiply it by g anyway, so it's the same thing. Again, remember, gravitational potential energy is just a type of mechanical energy. So where is the formula for GPE. It's on the back of the reference table, as you might have guessed, but if you're looking for GPE, I steered you in the wrong direction. All right, remember, it's delta PE in your reference table. And let's see. See, they have it over here. PE is equal to potential energy. Yeah, okay, reference table, but you're specifically really telling me the gravitational potential energy because I see the little g there. So why wouldn't you call it something different? And then PES is the elastic potential energy, the potential energy stored in a spring. That's why that S is there. And again, just as a sneak preview, we're kind of doing both at the same time, but that's what that formula is going to look like. All right, but for now we're doing delta PE or GPE. If you want, you could write GPE over here and EPE over here. Smaller than what I did it, just to remind yourself. Okay, so we have a 20-kilogram crate being lifted a distance of 5 meters. What is the gravitational potential energy of the block when it is 5 meters above the ground? And how much work is done on the crate? Let's write out our given information. So the mass of this object is 20 kilograms. The height or the distance that it travels is 5 meters in the air. We assume that we're on Earth, so we'll call it 9.8 meters per second squared. And for these energy ones, it's good enough to just give the magnitude of the gravitational field strength. That'll tell you how much energy is stored. And then it says, what is GPE? All right, so if you wanted to write it like the reference table, you can. I'm going to write it like this. This is totally fine. If you want to write it like this on my tests and quizzes, that's okay. If you want to go with what the reference table says, you would write delta PE is equal to all that different stuff. Oops, so this is 20. This is 9.8. And I was just thinking to myself, technically this is the change in the height, right? So what would that look like? The height final minus the height initial. Well, what was the initial height above the ground? It was on the ground initially. So the initial height was 0. And that's going to happen a lot. It's the thing is on the ground. And so that's where the initial height is. And then it's a height above the ground. So that's why, like, yeah, you could write delta H if you want. But, you know, most of the time, it's just going to be some height above the ground. In this case, it's 5 meters. So you do some multiplication, and you get 980 joules. I could have done that in my head, right? 20 times 5 is 100 times 9.8. Okay, so then we have the second question. It says, how much work is done on the crate? Previous to this, we've been saying, okay, I'm exerting a force upward, and that force must be equal to the weight. All right, so my applied force over this distance, and then you would just find the weight, and you use this weight as your applied force, and you can then find the work done. So the work is equal to the force times the distance, 196 times your distance upward or your height. So the work is still equal to 980 joules because the work, this is just another way of saying this, the work is equal to the change in the potential energy in this case. So if they're saying how much work is being done, well, it's just equal to 980 joules. And then you could even see, I wanted to point out, this is M times G, which is this, times H. All right, so it still works out the same way. I'm sure you get it. One way to kind of try to trick you would be phrasing it like this. It says, while riding a chairlift, a 800 Newton skier is raised a vertical distance of 500 meters. What is the total change in the skier's gravitational potential energy? And what is the work done against gravity? Okay, so if you want, you could pause the video and try it out. I'm going to start by drawing a nice diagram. So here is the ski lift. All right, it goes up, and here's the top of the mountain here. This is the ground. Oh, this is a horrible drawing. And then we have like a little chairlift. Okay, so here's the scenario. We got these people down here, and the chairlift lifts them to the top of the mountain so that they could ski back down. So the chairlift is doing the work for them. There's some engines that are doing the work in those chairlifts, exerting a force over a distance, right? So they could have been mean, and they said, oh, the length of this is maybe, I don't know, 1,500 meters. Maybe that's 1,500 meters. Figure it out. And it's at some angle. They would have to tell you the angle over here. Figure out what the work done against gravity is. Well, they're being lifted upward, right? They're being, if you're saying work done against gravity, how far up did they go? You would need to find the, I'm using all the colors today. This is a right triangle. If they gave you this distance here, that's the hypotenuse of the right triangle. And if they're saying work done against gravity, they're saying how far up in the gravitational field did you go? Okay, what is the work done against gravity? Yeah, these engines might be doing work against like friction. They probably have to exert more work than just the work done against gravity. But they're specifically saying what is the work done against gravity. So you would definitely need to know the height. And luckily for us, they do tell us, they say it's a vertical distance of 500 meters. Okay, that's pretty sweet. So how much mass do these people in the chair have? Like, how much are they lifting? Well, they say it's a 800 Newton skier. So let's see. We have the weight of the skier is 800 newtons, right? So how much work was done on that person over this 500-meter vertical distance? That's really kind of a different way to say that. So this is 500 meters. And we're doing work on Earth. So this is 9.8 meters per second squared. Okay. Actually, we don't even need this because we have FG in this case, right? So I would do GPE is equal to the force due to gravity times, so this is a separate term, times the height. You could write it like this, okay? I'm putting parentheses to show you that there's only two terms there that you need to multiply. All right, this isn't MGH, this is FG times the height. So you could just do it that way. GPE is equal to 800 newtons times 500 meters. So this person gained some potential energy. They gained 400,000 joules. Really, you would write 4.0 times 10 to the fifth joules. They gained a lot of energy. That engine brought them upward in the gravitational field, and now they have this much energy to play with. Plus, hopefully they had a nice breakfast and they have chemical energy stored in their bodies to use with their muscles. And what they're going to do is ski down the mountainside. We were skiing down the mountainside. The potential energy gets transferred into kinetic energy, and actually a little bit of heat between the skis and the snow. There's friction there, and it melts the snow a little bit. But mostly, you're going to go fast, right? But if you slow yourself down, you exert more of a frictional force. You're digging your heels into the snow and making it compact and melting it even more. You can transfer more of that potential energy into friction and go slower. You won't have as much kinetic energy. So it's all a balancing act, but you have this much energy to play with due to the ski lift and the operators, which is why you have to pay the ski place to allow them to use the lifts. Otherwise, you'd have to climb up the mountain and give yourself this much joules of energy, which would be difficult to do. Anyway, that's a nice little thing. Oh, and what is the work done against gravity? You could do it the same way. W is equal to FD. All right, so the force that you're exerting is 800 newtons over a vertical distance, the work done against gravity. So what is the vertical distance? Gives you the same thing. So it's a different way to look at it, but you're basically doing the same exact thing. Um, and that's all good stuff to know. Anyway, that's about it. Thanks for watching and have a great day.